Good morning, sir. Good morning, sir. Welcome, sir.
Good morning, sir. Nice to see you, sir.
Good morning,
How are you?
Sir, with you. Yes, sir. Fine, sir. Fine, sir. Sir, within 1 or 2 minutes, we'll join and start, sir. I'll call again.
Sure, sir. No, sure, sir. No problem.
Narendra?
Yes, sir.
Sir, good morning, sir.
Good morning,
Sir, shall we start,
Ramachandran.
சார் குட் மார்னிங் சார் எப்படி
Good
இருக்கீங்க
morning. நல்லா இருக்கேன். நீ எப்படி இருக்க?
நல்லா இருக்கேன் சார் காலேஜில் இருக்கீங்களா சார்
காலேஜில் இருக்கோம். என்ன ஆஃபீஸ் ஹவர்ஸில் டிஸ்டர்பிங்க நாங்கள்?
இல்லை சார் அதெல்லாம்
ஓகே ஓகே ஜிஆர்கே டேக் கேர்.
Sir, okay, sir. Okay, sir. Narendra, please.
Yes, sir. Good morning to one and all present here. I feel privileged to welcome you all for this workshop on design thinking, critical thinking, and innovative design. I hope you all gain something of importance from this workshop. Welcome to the present moment. Here, now, the only moment there ever is. I request Dr. G.R. Kannan, Professor, Department of Mechanical Engineering, to deliver the welcome address and to provide an insight on the theme of this workshop. Sir, mic, sir.
Thank you. Very warm welcome and good morning to one and all present here for the workshop on design thinking, critical thinking, and innovative design. On behalf of our chairperson, pro-chairman, principal, Institution Innovation Council, head of department, faculty members, program coordinators, Innovation Council student members, on my own behalf, I am very much pleased to invite our most respected resource person and our proud alumnus of our Mechanical Engineering Department 1995 batch, Mr. S. Ramachandran sir, Principal Consultant Manufacturing, Infosys Knowledge Institute, Bangalore. Welcome, sir. I would like to invite our most respected Principal Dr. D. Vasudevan sir and Dr. A. Vincent Anthony Kumar sir, MHRD IAC Coordinator. Welcome, sir. I also invite all faculty members and student friends from various departments of our institute and faculty members from various academic institutions. Welcome, one and all. So it is to disseminate the need of workshop on design thinking, critical thinking, and innovative design. As we are aware of that, our government of India is being circulated numerous technology-related challenges to student communities for developing solutions in various domains, namely health tech, automation, artificial intelligence, and virtual human and augmented reality, and blockchain and cyber security, then robotics and drones and transportation logistics and smart vehicles. In order to develop a solution or innovative design for any kind of problems, knowledge on design and critical thinking skills of our students are very much essential. Of course, design thinking is a human focused. We can simply say that the prototype driven process of innovation. This design thinking and critical thinking teaches how to innovate and how to make it out of our thinking, which are essential practices for our students or those who are applying for Smart India Hackathon or other competitions. So the design thinking workshops help our students team to create feasible and user-focused solution to design problems. Hence, disseminating the various stages of design thinking, critical thinking, and innovative design is a need of the hour, and also becoming inevitable factors for enhancing the problem-solving skills of our students. The workshops aims to bring awareness to our students about design thinking and also disseminating the suitable strategy to face the techno-related problems. With these few words about the workshop, We request all the participants to make use of the workshop in an effective way and implement the ideology while developing the solution for any kind of contemporary problems. Once again, I welcome our chief guest and all participants for this wonderful gathering. Thank you.
Thank you, sir. Leadership is the capacity to translate vision into reality. It is a great gift to have such a wonderful leader among us. I welcome our esteemed head of the department, Dr. R. Kannan, to address the gathering.
A very warm good morning to one and all present here. Today we have a joint venture with our department and Institutions Innovation Council. It is going to be a joint workshop on design thinking, critical thinking, and innovative design. If you are looking at the topics, I have mentioned the three topics. One is design thinking, another one is critical thinking, and innovative design. All are new to most of the people. It is a new topic only, but the process is something already we have experienced. Once when it is identified as defined this term, innovative thinking and the design thinking, critical thinking, etc. The need is basically how we are designing the things. In those days, when we were child, we were having only two cars. One is Ambassador, another one is Fiat. Ambassador models will be changed only after 15 years only. Every 15 years only, they will change the model. Till that, all the 15 years, we have to travel only in that car. Mark 1, I know about Landmaster, and then Mark 1, Mark 2, Mark 3. All the designs have been succeeded for 15 years. After that, if you are looking at the recent days, after 2000 and all, the design development has occurred in a larger way. In those days, Ambassador was making only one car. Entire plant will be on that only. But nowadays, if you are saying take Maruti or Skoda or any brand cars, that will be making every 3 months or 6 months or 8, 9 months or 1 year, they will change the version and they will call it as edition, special edition, this and that and all. So for all these things, we need a different thinking. There should be some difference from the previous model to this model. So how it can be achieved? It can be achieved only by engineers like you. Only you can do it. The creative idea, what you have, certainly your brain work, your creative idea, innovative thinking, that should be utilized. For that only, we conduct workshops like this. If we are taking our guest, Ramachandran, is a 95 mechanical engineering, our college student. Now he is in very good position, who can explain very well about this design thinking very nicely. So feel free to interact with him and get his knowledge. That's very important. Okay. If you are taking the design thinking, uses the designer's sensibility and methods to match people's needs. The need of the people should be considered with what is technologically feasible and what a viable business strategy can convert into customer value and market opportunity. Ultimately, we need to make money. How we are going to do that? By changing it. If you are looking at some bikes, what you youngsters are riding, there will be a minor change which will attract the entire college crowd. That design is very important. If you are taking the critical thinking part, it is the analysis of available facts, evidence, observations, and arguments to form a judgment. We have to come to a decision whether we can go with design or not. Innovative design part, it is a process of identifying, pinpointing, and understanding the needs of the user or audience. Ultimately, we go with the user. Whatever user, I want to have a red color point here. Yes, granted. Yellow color, granted. Like that, it should be done. So that is the things. We will have a wonderful session today. I thank in this opportunity. I thank IAC, Institution Innovation Council, and the resource person, the team of GR Kannan and the team members for arranging such a wonderful workshop. with our student, our alumni, Mr. S. Ramachandran. Once again, I thank him on this opportunity. You will have an enjoyable another 1 hour. Thank you for the opportunity given. Bye.
Thank you, sir. Successful people are not gifted. They just work hard and then succeed on purpose. It gives me immense pleasure to welcome our chief guest for the day, Mr. S. Ramachandran. Mr. S. Ramachandran is a principal consultant in the thought leadership team in Infosys, the Knowledge Institute. He is the lead for manufacturing and engineering domains. Mr. Ramachandran has more than 24 years of experience in the application of technologies for industrial usage. He is a regular blogger and speaker on topics like Industry 4.0 or the fourth industrial revolution, sustainability, servitization, reskilling, and future of work. He has co-authored a book titled Neo-Skilling for Digital Transformation along with Professor L. Prasad from IIM Bangalore. He is a mechanical engineer and a proud alumnus of PSNA College of Engineering and Technology. He did his master's in production engineering from PSG College of Technology and did his executive MBA from IIM Bangalore. He was a research student in Nanyang Technological University, Singapore, for a few years. He is a branding and communication board member of Society of Automotive Engineers, India. He led the editorial effort in publication for Confederation of Indian Industries ebook Women in STEM 2021, covering over 51 accomplishments. Sir, the stage is yours.
Thank you, Narendran. Good morning, everyone. Very happy to be here. Thanks to our HOD, Professor Kannan, also to Professor G.R. Kannan and the other organizing teams. It's always a pleasure to interact with the students of PSNA College. So let me share my screen. Yeah, I hope you can see my screen.
Yes, sir.
Yes.
Okay, good. So thank you once again. Very good morning to all of you. Very happy to talk about a very interesting topic, design thinking, with all of you today. So since it's a virtual session, it was intended to be a workshop. So I'll try to keep it as interactive as possible, given our time constraints, even if you cannot answer. But at least if I can get you thinking, that will be a job well done. So design thinking can very well be applied in many of your projects that you're going to do, whatever be your final year project or in between also. So what is design thinking? It is, if you look at the industry, basically there are two expectations, right? As Professor Kannan said, right, we'll talk about customer is the king. Eventually it comes to customers. But generally, if you look at industry, there are two broad types of problems. One is innovation, to come up with something new. You can come up with a product which nobody has thought of. That's one, right? That could be a new market opportunity for it. The other is in existing products or existing processes, there could be some challenge which you need to address. So design thinking will help you address both of those things, for existing problem solving and also to innovate and come up with something new. So this is the agenda for today's session. Before jumping into design thinking, as our HOD Professor Kannan said, right, not everything is new. It's many concepts that are already there that are put together in a nice way, and there are some interesting points also. But for you to appreciate design thinking, instead of jumping into it directly, I wanted to give you a quick overview of what are the other methodologies that are available in the industry, that are popular in the industry. You might have heard some of it, but then keeping them in context will help you to appreciate design thinking much more. So we'll start with what are the different innovation methodologies. So Lean Six Sigma are two very common methodologies. We'll look at them. We'll look at theory of constraints, and then we'll come to design thinking. We look at the basic principles of design thinking. We look at a lot of interesting examples, some from the automotive industry. We'll also look at TRIZ as one more innovation methodology. And then please stop me anytime you have any questions, because we wanted to make it like a workshop. So what are the approaches for innovation and problem solving that are popular in the industry today? These are global concepts, right? And like I said, two broad things: innovating for new things and problem solving where there are challenges in existing systems. So these are some popular examples. First is lean thinking. I'll take you through each one of these so that you appreciate it. Lean thinking is a very, very simple approach. Next, I can think of in the order of complexity is what is called theory of constraints. So lean thinking and theory of constraints are useful where there is a workflow. I'll give you a practical factory example since most of you are mechanical engineers. And then we will look at Six Sigma. Within Six Sigma, again, there are two approaches. We look at why it is called Six Sigma, but within it, again, we have the DMAC approach for existing processes and the DMA DOV approach for new processes or new products. And then we'll also touch upon TRIS. TRIS is again getting very popular. It's very difficult to explain it in one session today, but still I'll give you an idea. And if I make the bulb glow inside your mind, right? If I can arouse your curiosity, then the job is done for this workshop. So let's start with lean thinking. Some of you may have already heard this term. So what is lean thinking? Lean, as the name says, is basically about removal of fat, right? What is fat? Fat, when you think about engineering, manufacturing, mechanical engineering, it is about removing unnecessary tasks, right? So one of the popular tools that is used in lean is called value stream mapping. So let's take a practical example. You are making a product, right? Let's take a mixie as an example. It's a product which all of you can associate with. You buy a motor from a supplier. It's a very proven supplier, very good quality motors. You can innovate, like Professor Kannan said, what color you want, right? You come up with different mixie models. So this is how a very simplified version of your factory looks like. So you receive parts from your suppliers. You don't make all of the parts, like the motor and other parts, plastic parts are made outside. You store them in the factory. You inspect them for quality. Some machining has to be done. Final assembly is done, and then it is delivered. Now you are facing some issues, right? You are not able to make enough mixies to match the demand. Production is slowing. So you want to understand where the problem is. So one popular tool for this is called value stream mapping. So you take all the activities that are going on in the factory, and then what is the average time that it takes for each activity, and you split these activities into two broad categories. So one is value adding activities, other is non-value adding activities. What is value adding? Value adding, as HOD Dr. Kannan said, whatever customer likes, whatever customer values, whatever they are willing to pay for, those are value adding activities. The other is what is popularly called NVAs. So separate activities into value adding and non-value adding, and then look at how can you remove these NVAs. Now, if you ask me what exactly is an NVA, it is not just about scrapped parts or defective parts. So lean principle talks about 7 types of waste. So this again makes you think, if you really want to, whether you are an entrepreneur or you're getting into a multinational company or an Indian company in manufacturing, you should be aware of these basic concepts. The 7 types of waste. One is overproduction. So only the quantity for which there are confirmed customer orders should be made. There is a concept called just-in-time manufacturing for those of you who are interested in production. Japanese practice it very well. So even overproduction is a type of waste. Inventory of sub-assemblies, raw material, that is also waste. Motion, you would have done work study, right? When you see a person assembling something here, he or she should not unnecessarily move around. So the workplace should be ergonomically designed. So motion is considered a waste. Defective parts, over processing, waiting, transport, all these are different types of waste that are possible in any manufacturing setup. You can apply this in anywhere. It could be in a hospital, it could be in an education system. Lean is a very simple and generic method. So in this case, probably this inspection for quality may be a non-value adding activity which is taking up time. So you can implement some quality process at your supplier side itself. You can do some pokoyoka, or what is called foolproofing, to ensure that quality of parts from supplier is already inspected at their shop before it comes to you. So this is an example for lean engineering. You can value stream mapping is a tool. Now let's go to a little more advanced tool. This tool is called theory of constraints. This was made popular by this author called Eliyahu Goldratt. He's an Israeli. He has written this book called The Goal. So I would recommend you anytime to get a copy of this book and read it. If you read the book, right, it is almost like a fiction book. So the hero of the book is a factory manager. He faces several problems in manufacturing, and the author explains how theory of constraints is used by this author to solve his problem. So let's again go back to the same factory example. So the blue boxes that you see here are the products. Let's say it's a mixie, right? So you receive parts from the supplier, you store it, you inspect it, machining, all this happens. But like I said, there is heavy demand from your retailers. They ask you for so many mixies every month, every week, but you are not able to supply it. So you want to understand where is the bottleneck. So theory of constraints talks about identification of bottleneck. Where is the bottleneck? The very simple rule is whichever process has most processing time is a bottleneck. So you see here the motor comes, your knob, your switch, your body, all those things come, but eventually it is this machining process which takes up more time. Maybe this is the machining of the spindle for the motor. That's what connects the motor to the blade, which does the cutting action in the mixie. This process takes most time. Because of this, all the sub assemblies get piled up here, and you are not able to supply enough mixies to your retailers. So how do you address this? One simple way is to add another machine. So that way the waiting time gets reduced by half. So this bottleneck may go away. But bottlenecks cannot be completely eliminated. You need to do a balancing of workload between these different processes. This is a very simplified example I have shown, but I'm sure you can appreciate the concept. So we looked at lean engineering, where you identify NVAs and remove them. We looked at theory of constraints, where you identify bottlenecks and remove them. Now let's go to a more advanced tool for innovation and problem solving, which is now we get into Six Sigma. So within Six Sigma, like I said, DMAC is a popular approach. DMAC is an acronym. It stands for Define, Measure, Analyze, Improve, and Control. We'll look at each of those stages. So DMAC is an approach for existing systems. So you already have a baseline, you have a performance, you are facing a challenge from your customers or internally. You want to use DMAC to identify the problem, do a root cause analysis, correct the issue, and most importantly, control phase. You have to implement some foolproofing so that the corrective step does not go away after 1 month or 2 months. It has to be permanent. Tomorrow, some other problem may come. That's a different issue. So let's come back to this mixie example, right? So it's a very popular mixie. Its sale is very good, but suddenly you start hearing a complaint from some customers that it makes a lot of noise, right? Housewives are going to use this mixie. They are your customers. Customer is king, right? Whether it's an ambassador car, Fiat car, or a mixie. If your end customer is not happy with the product, it is a warning bell for you. So let's try to address this problem, right? So we take it up as a project. So this Six Sigma certification is very, very popular in the industry. When I joined General Electric, in fact, Motorola made this popular. I'll take you through some of the statistics behind DMAC, but then General Electric made Six Sigma very popular when Jack Welch was the CEO. I joined GE some 20 years back in 2000. Those days, it was mandatory for everybody to complete a green belt certification. So we used to run around for getting projects. Managers were under pressure. They used to be measured how many of your team members have completed Six Sigma certification. And then the next level, there was a black belt certification. So a black belt is like a 2-year full-time role. It is basically a quality role, but then you have to apply DMAC. I have been a black belt for a few years. The next level is to become a master black belt or MBB. It was very popular those days in GE. So if you want to really go up the corporate ladder and become a leader, you have to be a certified MBB. So there was a big rush for getting into the MBB role. You have to complete these online courses. You have to do projects, a lot of things that were required. So even now there are other outside bodies which offer certification in Six Sigma. So I was checking with Professor Kannan, J.R. Kannan. He said, as students, you have a basic exposure to Lean and Six Sigma, but still I'll touch upon it so that when we go to design thinking, you can appreciate the difference between the two. So coming back to this DMAC process, you have a mixie. This mixie has a noise problem. You put together a team of multiple people, one from engineering, one from manufacturing, one from purchasing department. You want to identify what is the issue and nip it in the bud. You want to correct the issue before it becomes a bigger issue. So the first step in DMAC is to define the problem. So the objective of the project is to identify the root cause for the heavy noise that is noticed in some mixers. Okay, now you start measuring it. So I'll touch upon this more. One of the core principles in DMAC is that data is very, very important. Generally, we tend to take a decision based on our experience, based on our intuition, based on our gut feeling. But when you come to industry, you have to throw out all those things. Those things are also important, but most important is data. Today, even politicians are talking about data, right? Anything you say, whether it is GDP growth, demonetization effect, whatever it is, where is the data? So same thing here. Some customers have reported that there is noise in the mixie. Is it because they are using it the wrong way, or is there really a problem with the product? So this team will start measuring the problem, right? We need data. So they measure the vibration. They take a sample, products, mixies. They test it in the factory itself, and they also notice that in some particular motors, the vibration is very high. In some mixies, they finally pinpointed to the diameter and hardness of the motor spindle. The motor spindle you saw in the lean, right? It is being machined in the shop floor. The diameter of the motor of the spindle in the mixie is what causes the vibration. Some of the spindles undergo a lot of wear and tear. There is too much of variation in the diameter, the hardness, right? Sometimes some you notice that you measure the hardness of the spindle, some are not hard enough as per specification. Because of that, the wear and tear is high, the diameter reduces, so the play between the spindle and the bearing is more, so it leads to a lot of noise. That is a no for your customers who are the housewives using this mixie. So variation is again a word which is very hated in Six Sigma. Again, we will look at that when we look at a normal distribution. So we have to reduce the variation. Now again, we have to go step by step in DMAC process. We have defined the problem, we have measured it. We know that the critical parameter to be measured is the diameter and hardness of the spindle. Now let's go deeper into it. It's called 5 whys. You have to keep asking why is the diameter varying so much? Why is it happening only in some spindles, not in all spindles? So one popular tool here is called a fishbone diagram. Some of you might have used it already. It's called by different names. It's called an Ishikawa diagram, root cause analysis. So there are different sources. It's called 6M's, right? It could be because of man, material, it could be because of methodology. So you do all that. There are some more popular tools called Pareto Analysis. A simple Pareto analysis says that 80% of the problems are because of 20% of those key issues. So we have already identified those 20% of the issues, which is a wear and tear of the diameter and because of the hardness of the spindle. So you have done the analysis. Now you want to improve it. So how do you improve it? So we have to make very stringent quality tests for both the hardness of the spindle and also for the diameter. So as all of you know, as mechanical engineers, we have done tolerancing, right? When you talk about a spindle diameter, let's say its value should be 1 inch plus or minus 0.001 inch, right? So maybe those tolerances have to be made stringent. Quality testing has to be made stringent. Maybe the heat treatment used for the hardness of the spindle was not sufficient. And you also find out that these are spindles that come from a particular supplier. So maybe that supplier was not trained enough in heat treatment, in machining, in quality inspection methodologies. So that is a control part. So for that particular supplier, in fact, you have to be proactive. You have to use this opportunity to check all suppliers and make sure that the raw material that comes from the spindle has undergone sufficient heat treatment. It is as per specification. You also implement a foolproofing method to make sure that only good quality spindles come. So this is DMAC approach. Now, so like I said, it's a Six Sigma is a very data-driven approach. So one very popular statistical tool that you will come across is what is called a normal distribution. So data, as you know, there are different distributions, right? Poisson distribution, binomial distribution, but the most popular distribution is called normal distribution. There is something called central limit theory. I'm sure you will cover all that when you read statistics. So normal distribution is most commonly seen in real world. Today, if we take the height of all students in PSNA college and you plot it on a histogram like this, you will see that it follows a bell curve like this. So on the left side, there is a lower specification limit. So this is again the diameter and hardness of the spindle. On the right side, there is an upper specification limit. And when you take a batch of spindles done in a month and when you plot it like this, at the center is a mean. So most of the spindles are at this value, let's say 1 inch, right? And at the same time, if you look at the x-axis, there is a variation. And what is used to measure this variation? That is the standard deviation. So there is a mean which is denoted by the symbol mu, and sigma is used for standard deviation. So what Six Sigma says, why is it called Six Sigma? It is called Six Sigma because you have to try to reduce the variation. Like I said before, variation is a taboo word. It's a hated word in Six Sigma. Nobody wants variation. Anything you take in life, right? Whether it's arrival of a train or a bus, you don't want variation. You want it to arrive on time. So same thing here. It's called Six Sigma because you have to try to fix 6 standard deviations between the 2 specification limits, which means your standard deviation should be really less. So most of the diameters will be around 1 inch. So what happens is your bell curve shrinks in size. You're able to fit 6 sigmas between the 2 specification limits. And the other parameter that is used is called a DPMO, defective parts per million opportunities. So Six Sigma translates to 99.7% accuracy or 3.4 defective parts per million objects or opportunities. So that's how important your quality should be. So organizations like Sundaram Fasteners, for example, they have already achieved this Six Sigma 3.4 DPMO type of objectives. Japanese companies are very popular for it. There was one popular joke about Japanese, right? All of you know how passionate Japanese are about quality. So when an American company signed up with a Japanese supplier for parts, they were told that you have to make sure defective parts does not exceed 3 or 4 per million. So the first batch of parts went to the American OEM, the original equipment manufacturer. So they said, here are the parts, and by the way, here are the 4 defective parts. So the Americans were confused. They said, what is this 4 defective parts? So the Japanese said, we are used to targeting 0 defects. You asked for a minimum of 4 defects. So here are the 4 defective parts. By the way, here are the 1 million correct parts. You can measure them. All of them will be perfect. So that's how important quality is. So in India, as engineers, as all of you graduate from your college, you should also strive for 0 defect. So when you study normal distribution, don't look at it as just a subject in maths, but it's going to help you long term in your career. Most of you may practice Six Sigma, whether you become a black belt or not. Today it's expected out of everybody. So normal distribution is used to measure data in Six Sigma. So try to reduce the variation as much as possible. Now we looked at DMAC approach. There was a mixie, it is facing a problem. Now let's say you want to design a new mixie for the US market, for example, right? Your mixie is selling very well in India, you want to take it to US market. So the approach followed is called a DMA DOV. So again, here define. What is define phase? You want to design a new mixer for multi-purpose home applications in the US. So US, as you know, is not 240 volts, it is 120 volts. And the pin that is used is going to be different. It's a square pin. All those technical issues you take care. What is measured? Already you know from the Indian market that the spindle had a problem. So you have already set a target to make sure it is of good quality. Analyzing, you foolproof the composition of the steel from your suppliers, your machining process, and then you design it. You design the spindle such that the tolerance is very close. You do some foolproofing, even if there is some minor variation, the bearing takes care of it. And then optimizing is a very important phase in DMA DOV in the process for new products. You optimize the diameter and hardness. You can say I want very high hardness, but it will cost you more. So there is always a trade-off between quality and the cost required. So you optimize it, and then you verify it. You do some prototypes, you test it. So it comes out as a very good quality mixie for the US market. You do a piloting there in US market. Unfortunately, you find that the product is not successful at all. It is a technically superior product. It works in 120 volts. It doesn't make noise. It's very quiet. It cuts vegetables. It does all that. But you find that it is not successful in the market. So why does it happen? We'll come back to this question. Let's use design thinking to see why this product was not successful in the market. Sometimes timing could be an issue. There are many technically superior products that were ahead of time. One example I can think of is what is called a Simputer. So Professor Vijay Chandru in Indian Institute of Science, he and his team came up with a handheld computer which was called Simputer. I think this was in the 90s, but those days smartphones were not very popular. So New York Times and other magazines identified it as a very high potential product, but unfortunately it was ahead of its time. There were no customers willing to pay for it and buy it. What use will it have? Those days nobody even imagined having a smartphone, what applications. So the product was not successful. It was not sold. It was technically superior. So we can think of many such technically superior products, but some of them maybe timing is an issue. They were ahead of time. We will look at Tata Nano, which had some other issues. So maybe application of design thinking could have addressed these issues and made them successful. So I'm not saying design thinking is going to guarantee successful delivery of these products, but it is definitely one tool which you should all be aware of. So keep this in your mind. We looked at lean, we looked at theory of constraints within Six Sigma, we looked at DMAC to correct existing processes. Your product is selling very well. We have used a DMA DOV process to come up with a new product, but it is not selling well. Let's come back to this issue when we look at design thinking. So just to close Six Sigma, right? So like I said, data is very important. So these are two gurus of quality and what they said. So Edward Deming said, in God we trust, for all others you need to bring data. If you go to your manager and say Mixi is making noise, so he will say what percentage of Mixi is it in a particular market? Is it in Madurai, Dindigul, Coimbatore? Is it because of supplier? You need to bring data. Peter Drucker is another guru. He said you can't manage what you don't measure. So this is very popular in the industry. What you don't measure, you cannot improve, you cannot control, you cannot even go to your manager. So collection of data is very important. And the moment you start collecting data, all those statistical measures come. What is the mean? What is the standard deviation? All that, right? So I'll quickly touch upon critical thinking also. I'll show you examples of many more types of thinking. But what is critical thinking? Basically, this is a long definition given by the National Council for Excellence in Critical Thinking. It's a very popular definition, but I will not go through it too much of English here. I've highlighted the important points. Evaluating information is very, very important so that it acts as a guide for belief and action. So, like HOD Professor Kannan said in the beginning, right? It's about decision making. In corporate life, you facing so many situations as an entrepreneur or as a manager. You need to make sure you practice rational, fact-based decision making. There should not be any bias when it comes to people. Some supplier, maybe he's a relative, maybe some other supplier you don't like. You should not let those type of biases come into your decision making. You should go only with data. Is the part they are supplying of good quality? Are they following the procedures that we have laid out? So these are the steps for critical thinking: observation, analysis, inference, communication, problem solving. Many of these tools, like normal distribution, these can be used across these techniques. There is no hard and fast rule, but there are some subtle differences which you should be aware of. So these are the skill sets required for to practice critical thinking. You need to know analytics. You should be good in communication. So one popular example for critical thinking is the nurses that you see in hospitals. So you know how many critical decisions they take every day, right? More than the doctor, it is a nurse who spends most of the time with patients, even more if they are in an ICU. So they do what is called a triangulation. So they have their own experience, right? Looking at a patient, they can say, okay, an experienced nurse, you would have seen it, right? They can quickly take a decision. I need to call a doctor, or I need to give oxygen. Their experience is one factor. The patient condition is one factor. There could be an ECG going on. They use a pulse oximeter. And then there are certain standards of care. If this is the situation for a patient, this is what you need to do. So nurses are one good example for critical thinking. Now let's come to design thinking. So what exactly is design thinking? This is a popular definition given by David Kelly. IDEO is a consulting firm which is very popular for practice of design thinking. So he says it's a human-centered approach to innovation that draws from the designer's toolkit to integrate the needs of people, the possibilities of technology, and the requirements for business success. So one big difference that you see, so far we saw Lean, Six Sigma, theory of constraints. We said data is very important, but when you come to design thinking, why it became very popular is because of the human element. So we'll again come back to the housewives issue, why they were not happy with the Mixi. But here it's so design thinking stresses upon the human-centered approach to innovation. So to close the other question, right? Why were the Mixis not popular in the US? So probably the families there in US are much bigger. The size was not sufficient. So your product is very superior technically, but customer is the king. If the housewife is not happy with the Mixi, maybe because of the size, or even if it's a very quiet Mixi, it cuts very well, but it was very small. So maybe they had to use it 2-3 times. Oh, this Mixi has come from India. You know how people look at Chinese products, right? So maybe family sizes are bigger in US. They use non-veg, they cut different things. So maybe the Mixi size was not sufficient. So just a small design thinking, just a small change in the design of the product can make your product successful in the US market. You need to provide them with a bigger jar, the motor, everything can work fine. So maybe that's a way to solve it. So coming back to design thinking, this Venn diagram that you see here, these are three very critical things required for your product to be successful. So the first is the people aspect or the desirability. Technology is anyway there. And the third one is business or viability. Like HOD Professor Kannan said, right? There should be a market who's willing to pay for it. So you make revenue out of it. It should be profitable. That is the business part. Now, the ideal situation is at an intersection of all three. That's where where a successful design thinking product will make sure all three aspects are addressed. Now let us look at some examples where only two of them were there. Let's take people part and technology part, right? So people are very happy with the product. It has been proved technically. One example I can think of here is the Hyperloop that is promoted by Elon Musk in US, right? So this area is called the hype bubble. There is a lot of hype in market. You would have seen it, right? So Elon Musk and his team, they are trying to sell the Hyperloop in India also for mass transit between Mumbai and Pune, for example. You know how it works, right? A tunnel is formed with vacuum. There is a capsule inside which moves at very high speed. It is very safe, but the problem is there is no business viability for it yet. How much will a person be willing to pay for, let's say, traveling from Chennai to Bangalore or Mumbai to Pune? And not many people can travel. So a lot of testing has happened. It has been technically proved, but there is no business viability yet. Now let's look at another example where there is viability and there is feasibility. So here, one popular example is a baby warmer example. I'll take up this example as detail for design thinking. We'll come back to this baby warmer example. The other one is where there is desirability and there is viability, but the technology was not there. One recent example I can think of here is the COVID vaccination. So the technology is immature. So now Bharat Biotech has finally delivered it. Mr. Krishna Ella and his wife have delivered it. But if you go back 6 months, right, we did not have a proper indigenously made vaccine from India, and we were dependent on AstraZeneca and other companies outside. So there was a very pressing need from people's side for a vaccination for COVID-19. The business was there, hospitals, people are willing to pay any amount of money, but the technology was not there. So these are examples where partially these three factors were addressed. They were not successful products. So we'll come back to this baby warmer example where the business need was there, the technology was not there, but the people's need was not fully addressed. So that's design thinking for you. Like I said, you can apply it in any project. We'll look at the stages of design thinking also, but keep these three things in mind. There has to be the people aspect of the desirability, the technology part should be there, the business part should be there, where you know what is the market segment, what is a proper price point, what are the competing products, what is the cost required to make it so that you are profitable. Even further, you should look at the cash flow part of it. Somebody should not take it on loan, you don't get cash at all, so you won't have cash to pay salary for your workers in the factory. So business need is important, people need is important, and technology need. So, like how we looked at DMAC and DMA, DOV, let's look at the stages in design thinking approach. These are the 5 stages, EDIPT. The first one is empathize. So, this is the human element where you wear the hat of an end user to understand how the product is used. So, in case of a mixie, it is the housewife. Maybe a housewife from US thinks differently from one in India or Asian countries. So, you need to put yourself in the shoes of your end customer to understand. That's what is called empathize. If you're not done empathize part, it's very rare for your product to be successful. And then you shall like DMAC, you define what are the end user needs of your customer. Maybe he or she wants a very quiet working mixie that can chop very fast, a powerful motor. And then you need to ideate, challenge the assumptions, think out of the box. We'll look at some practical examples of design thinking where out of the box thinking, you don't have to limit your thinking to products that are there today. As an engineer, as a very innovative person, you can come up with new ideas, new products that nobody thought of. So Apple's iPod is one example, right? It's such a small device, it can hold hundreds of songs. Steve Jobs thought of it. Where was the market? Before that, there was only Walkman. Before that, we had the cassette player. But iPod was a complete game changer, which nobody thought of. So that is why Apple is respected so much as an innovative company. And then you do a prototype, then you test it with some specific customers. So these are the stages in design thinking approach. Now let's look at the application of design thinking. So if you recall here, I spoke about this baby warmer example, right? So where, yeah, there is business viability, there is the technology behind it, but the people aspect was not taken care. So let's look at this baby warmer example, right? So this project was carried out by Stanford University. So here are some data points. Each year, some 20 million premature babies are born. Their birth weight is low, so the infant mortality rate is high. The doctors were not able to save most of these babies. This was prevalent even in Nepal. Kathmandu, as you know, it's in Himalayas. It's a very cold place. So majority of the premature babies that were born in Nepal, it was noticed that they were born in rural areas in Kathmandu. So the Stanford team wanted to address the issue. How can we save the lives of these babies? So the first thing the team did was, as you know, premature babies, they quickly develop jaundice, they get this yellow color skin. If you have been to hospitals, right, they usually keep them under an incubator or a warmer so that they cross over this jaundice stage, they become more stable, then they can be sent home. So the Stanford team, again, all very hi-fi engineers, they designed a low-cost incubator. This was tried out in the hospital, but it was not effective at all. Babies, the doctors could not still save the babies at all. Then they started applying design thinking. Then they started approaching the mothers of these babies. They found that most of the babies are from rural areas. One interesting thing they observed was that, Nepal, not a very developed country, electricity was not proper. So the problem for these mothers was keeping these babies warm at home, and more importantly, when they bring them from the home to the hospital. So all these were from rural areas. So it took some time to travel from the home to the hospital. So that's what they discovered when they did the empathize part, when they wore the hat of a baby's mother and looked at the problem. It was a completely different situation. So can you think of what was the solution that they came up with? So low cost incubator is fine. You can do any number of incubators. Providing an incubator at home may not work out because these are rural mothers. They may not be able to pay for the incubator. Even if they pay for it, will they have electricity at home? So what they came up with was a very, very interesting solution. It is basically a towel, a sort of towel which you can wrap around the baby. So what you see here is the actual product that was developed. So it is like a cloth towel, like a turkey towel, but there is a space in between. So these Stanford engineering students, they filled the inside of the towel with a type of wax, right? And what the mothers can do is they can use any source of fire to heat this wax. The wax will melt and it will stay warm for a few hours. So this towel was used to wrap the babies whenever they were at home, or more importantly, when these premature babies were brought from home to the hospital. So it kept the babies warm for a few hours, and then they can, by the time they go back, it would have become normal state. Then they can warm it again if required. So this is a very popular example for application of design thinking. So any amount of data, and these are Stanford students, any amount of data here would not have helped, but they had to practice application of design thinking to empathize who are the actual users of these incubators. It is not the doctor, it is not the nurse, it is these mothers and babies. So when they realize that these mothers and babies are from a rural condition, keeping the baby warm during transit at home, that's a big challenge. When they realize the true problem, they were able to come up with an innovative out of box thinking, right? Who would have thought that this type of a towel will reduce the infant mortality for uh, premature babies in Nepal? So this is a very popular example. Let's look at some more examples. So IDEO, I told you already, is a very popular company for design thinking. Their design of a computer mouse for Apple's iMac is a very popular example. When Steve Jobs was about to release a Mac computer in the market, he wanted a mouse, a pointer device, right? So he approached IDEO. So they are the ones who came up with, you would have seen the old mouse, right? There is a ball rolling inside. You can remove the ball. They took that ball from a perfume device or something. They tried it out. It became very successful. And then this child-friendly MRI scanner at GE Healthcare is again a very popular example. So you would have seen the MRI scanners, the PET scanners that are used in hospitals, right? There is a circular magnet which looks like a tunnel. There is a long bed which keeps going and coming. So generally, kids, when they look at it, they get scared, right? They are anyway claustrophobic inside a room, inside a hospital, you are scared. When you look at the scanner, they get even more scared. You have to stay still when you undergo the scan. So doctors face this problem. They apply design thinking. So again, think of it. How can you address this problem? How can you apply design thinking for this problem so that children don't get scared? And then this Oral-B electric toothbrush is another example. You'll find a lot of such popular examples for design thinking. Coming back to this MRI scanner, so an engineer in GE Healthcare again applied design thinking. He put himself in the shoes of the child who undergoes scanning. So what they did was they made it very colorful. They painted some Disney characters, Mickey Mouse, Donald Duck, all that. They made it very colorful. Earlier it used to look white in color, very scary, right? So generally hospital itself is scary. So this is again an example for application of design thinking. So these are some successful examples. Now let's look at some examples where probably application of design thinking would have helped, right? So one example I can think of is Tata Nano. So all of us know Mr. Ratan Tata had very noble intentions. Nobody doubts his intentions. All of you know the story of Tata Nano, right? When he saw a middle class family with father, mother, two kids traveling on a scooter, he thought, why can't I make an affordable 1 lakh car for Indian market? So that's how the Tata Nano story started. Probably they did a DMAC or a DMA, DOV approach for it. There was a target cost. He told his engineers, it cannot be sold for more than 1 lakh. I want a 1 lakh rupee car. So the car was made successfully. There was a lot of media splash around it. But what happened eventually to it? So in 2019, Tata Nano ended with zero production, and they said they are going to stop the production completely. So the big question there is, why did people not want the people's car? So as you know, there were some technical issues with it. There were some fire accidents. There was stoppage of production. All those issues happened. But most experts, what they feel was that it did not address the people's aspiration. Specifically in India, like I said, Mr. Tata's intentions are very noble. He had very good intentions, but probably car is seen more as a social status symbol in India. So nobody wanted to be associated with a cheap car, a 1 lakh car, right? So there is no clear proof for it, but maybe people did not buy it because of this. Later they tried to bring it in very flashy colors for the young market, for the youth, but it never caught up, right? So Tata Nano, although technically it was superior, it met all the expectations. There was an objective, the engineers met that, they were able to source parts, they engineered it, but it was not successful in the market because customers did not take it. So probably design thinking application could have helped Tata Nano. So here is one more tool to help you to map the customer needs to product features. So it's called QFD. QFD stands for Quality Function Deployment. It's a very, very popular tool specifically in automotive industry. It helps you to translate customer needs. First, you need to understand customer needs, and then you need to translate that into product features. So let's come back to the automobile example, right? If I'm making a master cars, and if I ask you, what are your needs? Again, we wanted it to be a workshop, but in the interest of time, I'll quickly take you through it. So let's say these are what the customers want, right? So voice of customer is very, very important. You need to have your ear to the ground, go to your retail showroom, talk to customers, be in touch with them, whether it's physical or on social media. So this is what you've gathered. Fuel efficient vehicle is the most important need for your customer. Here is a priority on a ranking of 5 to 1, where 5 is most important. Your customers say fuel efficient vehicle is most important. Comfortable travel is next. Safety is next. Infotainment. And the cheap and affordable car. Price of the car is the least priority. Of course, it is a priority, but the others are even more important. Now you need to do quality function collectively. You have your marketing team, which has gathered this data. You should have your engineering team, your manufacturing team, your procurement team, maintenance service, all of them. And these are the product features they came up with. So it might be difficult for you to read. I'll quickly tell you. So the first product feature is an efficient engine with an electronic fuel system, right? This is what makes sure the fuel is stoichiometrically correct. You get good mileage, right? And then you have a strong body in wide. The vehicle chassis is very strong. So Mahindra XUV 700 recently, they are going to use boron steel, high strength steel. At the same time, you cannot make a compromise on cost, right? It cannot become very costly. So you should know where to use the high strength steel. It is used only in the front portions of the chassis, which will come in impact whenever there's an accident. So as engineers, you need to be very creative, make use of tools like CAD/CAM, CAE, FAE to simulate the product and see how it works under different situations. Then you're going to use sensors for collision avoidance. You're going to use a lean approach where only the minimum number of features are required. Now you map all these product features to customer requirements. Wherever a particular feature will address a customer need, you put a tick mark there. Now when you take a weighted average, you will know what are the product features that are most important. And on top, you're going to look at the correlation between these different product features. If you want a fuel engine, maybe the weight of the car may go up. So that could be positive correlation, negative correlation. So eventually it looks like a house. That's why it's called a house of quality. And now these product features that you see, this will again come back as customer needs. So this will become what you see here as vertical columns will again become horizontal columns for the next house of quality. So that way I'm told companies like Toyota practice 7 levels of QFD or house of quality. So this is the first level, first house of quality. So these product features, again, they become customer wants for, let's say, your engineering team. And then they'll again come up with product features. For an efficient engine, For efficient electronic fuel injection, what is it that you need? For a strong body in white, what do you need? So that way, a quality function deployment is a tool which is very popular to translate customer needs into product features. So as you can see, these tools are all cross-applicable across different methods, whether you use Lean, theory of constraints, Six Sigma, design thinking. These tools are common. I'll quickly touch upon a few more approaches and then close the talk in the interest of time. So this approach, one more popular approach is called TRIS. TRIS stands for Theory of Inventive Problem Solving. This was made popular by a Russian inventor called Genrich. So what he found that problems and solutions are repeated across industries and sciences, right? So basically, it's about cross-pollination or cross-application of solutions across different problems. So he found certain patterns of technical evolution, and these innovations need not be limited to your own field. So these are the 4 steps that are popular in that are followed in TRIS. If you look at the bottom left, right, it starts with your problem, and then you abstract it to make it world's conceptual problems. You apply already solutions that are there across industries. So a problem in automotive can be addressed by a solution in, let's say, consumer goods or in aviation, and then you find a solution. But if you follow the traditional approach from left to right, you'll hit a roadblock, you'll hit a wall, you may not be able to solve your problem. So I'll give you, so in interest methodology, it's very interesting. So they have identified some 39 engineering parameters, starting from what is the mass of a part, what is its volume, what is the surface area, very basic things to more advanced things. So there are 39 such engineering parameters, and they've identified 40 engineering problems which can be generically applied. So I'll give you one very interesting example where TRIS was applied. You can ask me, this is all very nice, but is it really applicable? So one problem here was, the pizza, right? Pizzas are delivered at home today, especially during COVID time. You want it to be hot, right? And it also has to be crispy. But pizza manufacturers found that when pizzas were delivered from the oven, right, or Domino's Pizza, or whatever be the company, when it reached home, there was a lot of moisture formation inside the box, and the pizza became very soggy. So customers were not happy. The pizza has to be hot, and if it is going to be hot, there is water vapor in the atmosphere. There is water in the pizza also. There is going to be moisture formation. So how do you address this issue? And it has to be very cost effective. So TRIS was applied for this, and eventually, so they looked at the 39 engineering parameters. There were 40 common solutions. They applied that, and finally, what they came up with was they slightly raised the level of the box inside, which was used to place the pizza, and then they used some perforations in the box so that the moisture can go out. So today, maybe the pizza that you get delivered at home, maybe the box has been designed using TRIS methodology. So TRIS is one more methodology all of you should be aware of. It's not so simple to be explained in one session, but I wanted to make sure you're aware of it when we undergo this workshop on design thinking. So I'll quickly touch upon a few more approaches and then close this session. We'll open it up for any questions. So this is a term which my good friend in Mahindra & Mahindra, Dr. Shankar Venugopal, he's a VP for innovation there. He calls it the DESI approach. DESI stands for design thinking, exponential thinking, systems thinking, and inventive thinking. We have already touched upon design thinking. So this tells you how important this approach is, right? So we have seen enough of design thinking. What is exponential thinking? Exponential thinking is contrary to linear or step-by-step thinking. When you want to improve something, don't think of just improving it a little by little, right? That's called Kaizen, right? Continuous improvement is practiced in most industries. But exponential thinking, Peter Diamandis is a champion of this. So one popular example here is a chessboard story, right? So a poet went and sang a poem in front of a king. The king was very happy. He said, "What do you want?" So the poet said, "I want 1 grain of rice in the first square of the chessboard, and then you double it. In the next square, I want 2 grains. In the third, I want 4 grains. That way, keep doubling it." The king said, "What is the big deal? I will give you." So he asked his minister to give it. The next day he asked, and he said, "What happened? Did you give the grains to the poet?" He said, "No, Your Majesty, we are still counting. If you actually do it right, by the time you reach the 64 squares, you don't even have to go so far." That's the power of exponential thinking. The number of grains of rice has become so many that the king was not able to deliver it at all. So exponential thinking, be aware of it. Systems thinking, again, this is IEEE's definition of systems thinking, where you look at a product as a combination of smaller subsystems which work together. In case of the mixie example, there was a motor, there was a spindle, there was a blade cutting system, there was a jar, there was a body. Each one is like a system which has its own behavior. These systems interact with each other. So when you look at a product as a combination of such subsystems, that's where you start practicing systems thinking. Again, it's a very broad topic for me to cover on this in this session, but I'll close with this and open up for questions. So in the context of design thinking, like I said, empathy is the most important part there. The human connect is most important. However good you are technically in coming up with products, you should not miss the customer. So customer is king. That's one takeaway. And while you know about design thinking, make sure you are aware of other equivalent approaches that are also there in the market. So you cannot give up data just because you are practicing design thinking. And these methodologies are very much applicable for you. You can apply it whether you want to design what should be the frequency of arrival of buses from Dindigul bus stand to our college, or you want to design a product, a mobile app, whatever it is. Design thinking is a very generic approach which you can practice. I gave you several examples from automotive industry and other industries where you can practice it. So with that, I hope I am on time. I will close this session and open it up for questions. Thanks again to our HOD, Professor Kannan and Professor J.R. Kannan, for this opportunity. It's always very exciting to share thoughts with our students. So thank you so much. I'll stop here.
Narendra?
Yes, sir.
So, dear participants, the session is open to questions, queries. If you have any queries, please discuss to our resources.
Yeah, Harigan, I'm faculty in the Department of Mechanical Engineering. Regarding the TRIS, what you said, is there any upgradation from the evolution? Because TRIS is a concept that has been developed in 1945 or 1950, and we have more TRIS schools in Mexico and Russia. But what about the importance of TRIS in India, and how far it is being updated, or is there any contradiction that has been added up in TRIS?
Yeah, good question, Professor Harikandan. So, TRIS, like you said, right, the founder, it was started in 40s, 50s, but they have developed these concepts over so many decades. It is definitely very popular. So, a very good friend of mine, Mr. Tito Krishan Bemuri, right, he was a colleague in General Electric. So, he's like a point of contact for application of TRIS in Bangalore. There is an association for it. So, he practices it very often. So, I can connect you with him. So, to that point, it's not a closed chapter. Those concepts are already developed. They are already proven, but they keep improving upon it, and they find newer and newer applications for it. It's still very popular among industry. So I know he goes to a lot of companies like Mahindra and Mahindra to train their employees in application of TRIS. So yes, it's an evolving field. It's pretty hot. It's very popular in the industry.
Thank you, sir. Thank you.
Any queries, sir? Any queries? Okay, there is no queries, then we can wind up the session. So, Narendra, please.
Yeah, dear Kanan sir.
Yes, sir. Yes, sir.
Okay. Very nice to meet you, Mr. Ravachandran sir. I think it's a wonderful
Hello, sir.
session. Yeah, hello, sir. Yeah,
Hello,
wonderful
Professor Wilson.
session.
Hello, sir. Good to see you, sir.
Yeah, thanks to, I think, deliver a wonderful talk. I think just I'm joining the beginning, and you are very much, our students are interested, and they were given a wonderful lecture about the design thinking, and especially how the GE electrical experience, the healthcare, the how the design making thinking about the children, how the children are a little bit finding difficult to the MRI scan, and so how this environment is changing. And as also, I think given some talk about the innovative thinking.
Yes, sir.
The last slide, and how whether we have any other the material for the innovative thinking or any other. I think the last slide, if you come across the last slide, and
I can share some material. So there is a lot of material for these different approaches. More important for our students will be to get the basics of it, but apply it and see.
Oh.
So there is a lot of material available. I can share it with you or Professor G.R. Kannan.
Yes, since everyone is talking about the innovative process, and they are going for the pattern and other things. So it may be good for the students. They can think about how I think we talk about the design and the potential and other things, and the innovative thinking also. So thank you very much. I think it's a wonderful session. On behalf of the PSNAC team, Institution Innovation Cell, I thank Mr. Ramachandran. Dear sir, please proceed.
Yes, sir. Yes, sir. Narendra?
I now invite Mr. Yerni B, second year mechanical engineering, to propose the vote of thanks.
Gratitude is the most exquisite form of courtesy. On behalf of the Mechanical Department of PSNA College of Engineering Technology and the Institute Innovation Council, I would like to thank Mr. S. Ramachandran, Principal Consultant Manufacturing, Infosys Knowledge Institute, Bangalore, for inspiring and encouraging us with your words on this special day. I would like to express my gratitude to our Principal, Dr. D. Vasudevan, for permitting us to organize a function even amidst the pandemic. It's my immense pleasure to thank Dr. R. Kannan, Professor and Head Department of Mechanical Engineering, for his continuous support. I would like to thank Dr. A. Vincent Anthony Kumar, Professor and Head Department of Information Technology, for helping us to organize this event. I'm honored to thank Dr. G. R. Kannan, Professor and in charge of IIC Mechanical Department. Once again, my sincerest gratitude to all the students for making this grand success. Thank you all.
Thank you, sir. Thank you for a very good.
Thank you, Hani. Yeah, thank you, Professor Kannan. Yeah, nice meeting you.
Ramachandran, thank you.
Thank you, sir. My pleasure, sir.
Right, and the first slide போட்டல சில ஒரு நாள் எடுக்க சொல்லலாம். ஜிஆர்கே
சரி சார்.
And what are the methodologies used for design thinking போட்டல tools. அது வந்து கொஞ்சம் நல்ல பசங்களுக்கு இந்த இன்ட்ரெஸ்டிங்கா இருக்கும்னு நினைக்கிறேன். If you are going with the case studies.
Correct, sir. இது ஒரு டாபிக்குமே you can do a separate session.
அந்த மாதிரி அதுக்கு ஒரு சீரிஸ் போடலாம் அவனே ஜிஆர்கே.
சரி சார், பண்ணிடலாம்.
நம்ம பசங்க வந்துருவாங்க, 7ஆம் தேதி வந்துருவாங்க. அதுக்கப்புறம் அந்த ஆன்லைன்ல கொஞ்சம் போட்டு ஹாலில் உட்கார வைப்போம். Okay.
So what will be more interesting is if they start practicing. ஏதாவது சின்ன project, final year project வரைக்கும் கூட வெயிட் பண்ண வேண்டாம். Whenever they get an opportunity, if they say we have practiced design thinking and we did this, then அவங்களுக்கு கான்ஃபிடன்ஸ் இருக்கும். It will give them a lot of good exposure.
Exactly. அது பண்ணா போதும். அது சொன்ன அந்த ஃப்ளேவர், நீ சொன்ன மாதிரி இந்த ஃப்ளேவர் கொடுத்தா போதும். அப்புறம் காபி சாப்பிடுறதுல அவன் சாப்பிட்டுருவான் அவன். That will be
data plus is a human element part. Yeah.
Yes, surely. Right, thank you பாப்போம்.
My pleasure, sir. Nice talking to you, sir.
If time permits, in person வாங்க.
பாப்போம் சார், கண்டிப்பா.
கிட்டா பாப்போம். உள்ளாச்சி தானே.
நீங்க அப்படியே வந்துட்டு வீட்டுக்கு போயிட்டு I think we can have some one day session for the faculty members also. I think we can give.
Sure.
Not only the students, faculty members also. I think they are very much interested in the design thinking with the problem solving and other areas too.
So actual workshop apna inu interesting irukku. We can take some real problem.
Yes.
Form groups, let them come back and present. And the mari we can make it very
on table product வச்சு dismantle பண்ணி மாட்ட வைக்கணும். அது பண்ணோம்னா ரொம்ப அருமையா இருக்கும். ஒரு நாள் பண்ணுவோமா? ஜிஆர்கே
சரி சார்,
இன் பர்சன் ராமஜன் என்னைக்கு ஊருக்கு போறாங்கன்னு கேட்டுக்குவோம். அன்னைக்கு உள்ள
சரி சார், இன் பர்சன் பண்ணுவோம்.
Okay, we'll do that. Thank you.
Okay, sir. Have a nice day, sir. Take care, sir.
Anything ரொம்ப சந்தோஷம். Happy.
Thank you, sir. Bye.